We are now going to download the example data. We will download the FASTQ files and then the reference sequence. So let's do that. Let's go to the page where I showed the original tutorial. We will get the download links there. So let's go to that page. Okay, so on that page, just scroll down. There's an outline here. So let's go to this side here, get data. We will get there and then we will scroll down. We will see the data set. So these are data sets. For this tutorial, I'll use a single sample. So I'll use the first one, which is father. Because we are dealing with paired end reads, we will have read 1 and then read 2. So we will download all of them. To download, you can use your browser or you can use the command line. If you want to use your browser, just highlight that link. Just right click it and then just open it. You can open it in a new tab as well. So once you open the link, you will be asked to save files. So we will do it one by one. So that's how you do it with the browser. But I will do everything on the terminal. So I'll just copy the link. I will start with the read 1. I'll copy it and then I'll move to the terminal to download it. So let's proceed. Okay, so on the terminal, I'll first create a working directory. This is a practice I always recommend. The reason why I want to create a directory is that I want to make sure all files that will be generated during this exercise will be separated from files that exist on my PC. This will prevent me from accidentally modifying files. So I will say make the variant colon and then I'll cd into it. So this is my main folder or my main directory. And then I'll say make the data. And I'll also say make the data / FASTQ. Perfect. So that's what I have here. So the data directory, there's a sub directory called FASTQ. This is where we will store the FASTQ reads. So now that we have this, let's download the read 1, the one and that's we copied its link. So we'll say regets. I'll use regets, but you can use any other downloader to also get the files. So that's it. So I'll say reget -p and I'll say data / FASTQ. So -p here will tell reget that we want the data to be downloaded into this directory. Okay, so this prevents us from downloading it first and then moving. So we will do everything here. So I'll supply it with a link and then I'll run this command. So I'll do that now. The file has been downloaded. So if you do an ls data / FASTQ, you'll find the file there. Now let's download it with 2. So let's go and get the download link. So I will copy the link and then I'll go to the terminal. On the terminal, I'll say reget -p data / FASTQ and then I'll supply the link. Then I'll execute this command. Okay, so that file has also been downloaded. Let's check it out. Let's proceed. Let's do an ls data / FASTQ and you will see the files there. So that's about it. Now let's download the reference sequence. Let's get a link. So on this page, just scroll down it, and then you see it there. So this is the reference, the reference sequence. We are using chromosome 8, HJ19. So I'll just use this link. Notice the .gz. This means that it has been compressed. Okay, it's compressed. So we will download and then we will decompress it. So let's go to the terminal and download it. On the terminal, I'll create another directory. So I'll say make the data / ref. Then I'll say reget -p data / ref. and then our supply we get with the download link. So let's download this. Okay, so it has been downloaded, but because it's compressed, okay, we need to decompress this. We want the uncompressed file. We want the FASTA file. So let's first do an ls. So I say ls data/ref. So this is it. So we want to decompress it and get the original file. So I'll say gen unzip data/ref/agent19. Yes, and then I'll execute this command. So this should do the job for us. So let's do an ls again, data/ref. You see the file there. So this is the FASTA file. Okay, this is the reference sequence, and we are going to use that later on. So now we have the data we need for this exercise. So let's proceed. The next thing we will do is map the reads to the reference sequence. That is what we have here. So we are going to use BWA. And we will use the bwam command to do that. So let's go to the terminal and continue from there. Okay, we are now going to perform genome mapping. But before we perform genome mapping, we also need to index the reference genome. So let's look at how we will do that. Let's clear the screen first. Let's check our reference genome. This is our reference genome. We are going to map the reads to this reference genome. And as part of the mapping activity, we will need to index this reference genome. So let's do the indexing first. So we say BWA index. We say data/ref/agent19. This one here. So let's do that. So indexing has been done. Okay, we have the indexing done. So we'll proceed. So if you do an ls into the ref directory again, you will see that some files have been generated. So let's say ls data/ref. You see that other files have been generated. So we need to have these there. Now we will perform the mapping. So let's proceed. Before we perform the mapping, let's look at the data again. So ls data pascal *star.gz star.fq.gz. We just want to highlight only the FASTA files. So we have them there. There's something I want you to take a look at. Look at the file names here. You see what we have here. You also see this. So in my opinion, these are long file names. Okay. So what we will do is to assign these names to variables so that we will have the names shortened for us. So we will do that. We're also going to do the same for the reference genome. So let's say ls data/ref. We will do the same for this one as well. So let's do those ones first. So first of all, I'll say ref equals data/ref/hg19 chr8.fa. I will do this one first. And I will do the same for read1, read2. So read1 equals to data/pascal/father r1.fq.gz. So let's do that. And then read2 equals to data/pascal/father r2.fq.gz. So we have them done. So we are ready to go. Now, aside these ones, we also need to make sure we add read groups. Read groups are important. So the read groups, we will include the sample ID and then the sample name. Let's go back to the Galaxy page and I will show you what I'm talking about. This is the Galaxy page. So Yeah, it says that we should set read groups. That is what it means. So we are going to use the information here. So this will be the ID, the sample ID, and this will be the sample name. We need to add that. So we will proceed with that. It's important to do that because some of the variant callers require you to add read groups to your BAM file, the BAM file that you generate. Okay, so it's important to do that. So in the process of mapping, we set the read groups and then BWA will just add them. So let's proceed. Let's go back to the terminal. Okay, so let's set the read group. We will need to create some variables here as well. So the first one will be the sample ID. So I'll say RGID. That's for the sample. I'll say RGID equals 000. And I'll say RGSN. That's for sample name. I'll say father. And now we are going to set the read group itself. So let's look at the script here that I prepared. So I am going to set the read group using this one here, this particular text here. So I'll just copy this. This is the script for this tutorial. And if you want to download the scripts, you can check the description box. I'll leave the download link there for you to get it. So that's it. So I'll just copy this. This is what I'll use. I'll explain something here. So I'll copy this there. I'll leave this text also in the description box. So you don't need to type everything. Just go to the description box and you'll see this there. So just copy everything there. Let's go back to the terminal. So on the terminal, I will say read group equals, and then I'll paste this there. So here, there's what I want us to discuss. This dollar and then the RGID in curly brackets is telling bash that we want the actual value. You know, RGID is a variable. That's what we had here. So what we have here is the actual value, which is 000. That will be placed here. And then the RGSN, that's sample name, that will also be here. So this here is what this one here. So that is what we have here. So we've set it. We've not started the mapping yet. We are only defining the values that we will use when we are finally setting the read group. So that is what we have here. So let's run this command. Okay, so that has also been done. So we'll proceed. So now if you do an echo $read group, this is what you see. You have everything there. So this thing here is what we will use. So that is what the read group. Okay, so we'll proceed. The last thing we will do before mapping the reads is to create a directory. This directory will be used to store the output files. So we'll say make the, it should be in lowercase, make the BAMs. We are going to generate one BAM file, but we will process the BAM file and then generate additional BAM files. So that is why I am using the name BAMs. I have that done. Now we are ready to map the reads. So I say BWA mem-t and then I say 8. This is threads. If you have more CPU cores, you can increase this. You increase this, BWA will run faster, but I am using 8. I'll now say -r and I'll say quotes $read group. Then I'll add my second double quotes. I'll now say $ref. I'll say read 1 read 2. So that's what I have here. This entire line here, this particular codes here, these codes, okay, the command here will generate alignment records. And so we need to also specify an output file. Okay, so what we are going to do is that we are going to add an additional command which will save everything as a BAM file. So I will just add my pipe command and then I'll say SAMTOOLS view -h-b, and I'll say -o for output. I'll say bams/father.raw.bam. I'll use this. Let me also say that the strategy we are using here is useful, especially if you are running lots of samples. So if you're running lots of samples, then along the way, you can just assign the file names to the variables here and then use that here. Okay, so that's what we have. Now, if you are dealing with lots of samples and you are having a challenge, you can still contact me and then we can just arrange and then resolve that issue. So just make sure you do that. Now let's proceed. I have my final command, so I'll execute this and then generate the BAM file. Okay, so let's wait for BWA to map the reads. Okay, read mapping has been done. So let's proceed. So let's do an ls into the BAMS directory. And then we will see this there. So this is the BAM file. This is the raw BAM file. So that's what we have here. I named it raw because we will process this BAM file to generate our final BAM file. So that's it. Now, after read mapping, it's advisable to check the statistics, okay, the mapping statistics. So let's do that. So you say SAMTOOLS flag stats, and then that is just 1T. So flag stats, and then we say bams/father.raw.bam. So this will give us some mapping statistics. So let's run this. Perfect. So it will tell us the percentage of reads that's mapped to the reference sequence. Okay, so that's what I have here. I'll just focus on this one here, the one that's mapped. So we have majority of the reads mapping to the reference sequence, which is good. Okay, so this statistics will help you, okay, to kind of understand what has happened in terms of the number of reads that's mapped. And ideally, we should have majority of the reads mapping to the reference. This will let us know that indeed we are dealing with the right organism. So that is something you have to also look at. So if, let's say, you are dealing with human genomes, you perform your read mapping and realize that most of the reads, or quite a substantial number of the reads, are not mapping to the reference sequence, then you should investigate further. That means probably something is wrong. It could be contamination, it could be sequencing error, etc. But you just need to make sure you check that as well. So that's about it. Now let's proceed. We have our BAM file generated. What we are going to do next is to filter the alignment records. I made mention of that. Now let's go back to the Galaxy page. I am following the tutorial, so I am trying to make sure I reproduce everything that has been stated in that particular tutorial. So let's go back and check the next step. So if you scroll down, it says mapped reads post-processing. So let's look at it. So for the post-processing, we have some description here, but I'll skip that. I'll come to this one here because that is what is of interest to us. So we will filter the mapped reads. So here, what we are going to do is that we are going to filter using the flags. Okay, I'll give an example here. What we are going to do is that we are going to remove reads that are not mapped to the reference sequence, and we are also going to remove reads which have their mates unmapped to the reference sequence. So that is what we are going to do now. So let's proceed. So let's clear the screen first and then filter the reads. So we will say SAMTOOLS view -b-f. The -f, the F here is uppercase because we are using that to exclude some reads. So we say 0xc. This is hexadecimal. Okay, this is used to exclude reads that's the non-map, and also reads with mate pairs that are not mapped to the reference sequence. So that is what we are doing here. We specify the BAM file, which is bams/father.raw.bam. Then we specify an output. So we say -o. We say bams/father.filtered.bam. Notice how I use the same sample name, but then the extensions here are different. So the extensions are used to differentiate the outputs, okay, for the different steps. So that is what I have here. So I'll run this to filter the reads. Okay, so we have done the filtering. So let's do an ls into the BAM directory, and we will see that file there, the new one we generated here. So we are ready to go.